There we go. Now I'm recording the way I want to. Okay, so now we've got the recording running. Let me just briefly introduce our guest speaker today, Mr. Shawn Martin. Mr. Martin is a UF mechanical engineering graduate and alum from 1986, and has from that time until now, he'll walk through his background with you, but he's essentially worked for the Department of Defense, for the military and the government, retired, and now actually went back to work as an engineer for a company that does contract work for the Department of Defense. And his presentation today is going to be on TRLs, technology readiness levels. And I thought this is probably a good time to introduce you guys to TRLs, because you're now kind of transitioning out of 4501, and hopefully we'll see you in 4502, where this entire semester you guys have gone through the process of a paper design. So as we'll see in Mr. Martin's presentation, sort of low level TRL type work that you guys are doing in this class. And you'll be transitioning into prototype development towards ultimately the creation of what we hope is a commercial product by the end of 4502. And so basically taking your ideas from 4501, which were low TRLs, and elevating them up higher on the TRL scale. And so having Mr. Martin come in and give a presentation kind of on TRLs, what they are, how to characterize technologies on that scale, seemed a very natural way to facilitate the transition from 4501 to 4502. And of course, he's out in the real world doing this for real. So he provides a perspective that is an academic inside the institution. I don't have the experience to provide. So I think that's important as well, as you guys are producing a commercial product for a potential customer. So with that, let me get out of the way and let Mr. Martin take over. Shawn, you should be able to share your screen.
Gotcha. Can I get a mic check?
I can hear you.
You can hear me? Okay, I can hear myself. Oh, okay. How about now?
I can still hear you.
That's a good thing. I just can't hear myself. Okay. I can, I guess it'll bounce around between the ears well enough. Let me share my screen. Okay. Perfect. Come on. All right, cool. Let me move this little box out of the way. All right. So what time do we have until, Professor?
Until 4:55.
4:55. Okay, great. Perfect. Okay. Yeah. Excuse me. As Professor Trump said, my name is Shawn Martin. And before I get into the lecture, if you will, the material, just a little bit about me. As he mentioned, I was a 1986 graduate of the mechanical engineering program that's prior to the merger with aerospace. In 1986, May 3rd of 1986, in the O'Connell Center. And years later, went on to get my master's degree in national security and strategic studies from the Naval War College up in Newport, Rhode Island. And for the business that I'm in Department of Defense, that's a very good degree to have. Maybe not if I was making coat hangers, but with the world that I serve, it certainly does. Real quick, I was a member as a student here in the American Society of Mechanical Engineers student chapter, 1 year as a program chair and the next year as a vice president. And then the following, when I graduated and moved to Bay County, Panama City, that is, I became a member of the Bay County professional level group of ASME and served offices as program chair, vice chair, and chair. And I mentioned the latter just because I think it's really important for each of you to build your network of connections professionally. And this, excuse me, is a easy way to do it by joining a professional society and attending events and so forth. That's how I did it. It brought me a lot of connections, which helped me along the way. My first job out of UF was as a facilities engineer with Southern Bell. And as I've mentioned to the other two classes today, I hated the job, and that's okay. It allowed me to understand what I don't want to do. And so I was only there for a year. And through my network that I was slowly building, was able to secure a job with the Navy. And that's the NSWC-PCD. That's Naval Surface Warfare Center, Panama City Detachment. And I worked there for 10 years as a design engineer. And from there, I went to U.S. Special Operations Command down at MacDill Air Force Base in Tampa. I'm not sure if any of y'all know who SOCOM is, U.S. SOCOM, but it's the headquarters for all of our military special operations units, Navy SEALs, SWICs, Green Berets, Rangers with the Army, Regiment Rangers, and Raiders for the Marine Corps, Combat Controllers, PJs with the Air Force. But it's the headquarters for them, but it's also the headquarters for developing unique equipment for them. So that's for the last 24 years what I've been doing. Responsible for directing and executing, developing technology and capability for special operations specific. As the professor said, I retired in May as a government service employee after 34 years and became a support engineer with Apogee Engineering. So I'm back in the undersea office at SOCOM, supporting dry combat submersibles, which I'll talk later on about, but very much so now as a supporting role as opposed to being in charge. So a very different capacity. And special skills, as it says there, excuse me, I went through Navy dive school as a civilian in 1988, 1 year after joining, working for the Navy, and then again with the Marine Corps as a combat diver in 1994. So a bit specialized skills, but they play out very well in the undersea world, which I support. All right. So moving on, and I'm sorry about my voice, but it's starting to leave me after the first two classes. So I'll go through real quickly today definitions of technology readiness levels, why it's important, I think, case studies, and Q&A. And we can do Q&A along the way. Please, if you have a question along the way, don't wait until at the very end because we may run out of time. And one caveat I will say is that any of the photos in this presentation we're taking off of the internet, excuse me, the internet, and they're in the public domain. I do not have the authority from my command to disclose anything that's not in the public domain. So I'm made sure that all the information I provided today was could be found on the internet. Okay, so technology readiness level, it's just really a tool, basic top level tool, if you will, to understand where you're at in your design or technology development phase. And so going from the concept phase into more of a prototype material phase and in maturing it into a product. So it kind of covers from basic principles through concepts, various levels of prototypes, and into a final product. So prototype can have a variety of definitions, and it's a little bit of a gray term, but I'm giving you the Wikipedia version here. And basically it's it can be hardware, it can be software, if you will, or it can even be a process, but a prototype process, something to demonstrate a concept or an idea in a material sense or actually a process sense. And excuse me, it's intended to mature ideas and concepts into a final, more mature product. And I know it's a bit of a nebulous definition, but just kind of skipping through this or going through this. So here's a quick example of what I consider to be proof of concept prototype. And who knows, it may not be. And this may have been the end game of whoever designed this and put it together just as a fun little thing to run around with. but it could be just a basic proof of principle prototype for a small scooter or motorcycle, but sort of illustrates what a prototype can be. It can be far more refined than that, or it can be just a subsystem of this motorcycle, if you will, that's in a laboratory environment, but far from a final product. So we'll move on. So, excuse me. Technology readiness level really started from a formal sense by NASA during the Jupiter orbital spacecraft program. They were having problems with different team design members and a common understanding of what technology maturity levels were. And so what they set out to do is come up with basic level definitions, if you will, for different TRL levels for the individual design teams and the program manager or the engineering manager understand where the level of maturity was of critical components, really. And what I mean of a critical component, let's say an analogy for your car, your brakes would be considered a critical component. An interior dashboard trim piece, for example, is not a critical component, but a critical component is it is relied on for the basic functionality and safety of a device. So brakes would be considered critical components. So all this is really wrapped around critical subsystems or components of the device. And TRL has been adopted by the Department of Defense, Department of Energy, and a variety of other agencies. So this is the basic chart that when you look up NASA TRL, that's what you'll get. And you can see here, I grabbed this off of Wikipedia. It's kind of an inverted chart, Scott. On the left, description level 1 through 9, and on the right, the little graphic is 9 through 1. So it's a little bit inverted, but don't let that bother you. But you can see level 1, which is the most basic level, is really talking about basic principles and going into concepts and so forth. And then moving on, say to level 4, key elements, or if you consider element or component, demonstrate in a laboratory environment, and then key elements demonstrated in a relevant environment. And I guess where you're going from your paper study or your design to next semester will be going from, say, a concept study level 3 to a level 4, even perhaps a level 5. Excuse me. But it's really, really important to understand these steps and where you're at for many reasons. And I'll try to provide some more in-depth explanation as we go. But does anybody have any kind of top level questions so far for what I presented? Okay, crickets. They must be just spot on and so obvious, crystal clear, obvious, huh? So anytime I ask a question, it'll be good. It'll be good. Here's another representation of TRL. This is not the NASA version, but I think this is a good one to help you understand where universities fit in typically with technology development versus industry, and that each hash mark, if you will, or chevron represented a progressing level of maturity, and below it, it gives you a slight definition, if you will, of where it's at. But many of the things between 4 through 7, sometimes that's called the valley of death. Sometimes it can actually be just between 5 and 8, the valley of death, where it can be demonstrated, a technology can be demonstrated in a relevant environment, but industry or even program managers within the military where I'm at, they really don't want to pick up anything until it's a TRL 6 or 7 at the lowest, because it means risk to them. So fundamentally, program manager will not pick up anything that is below a TRL 6 by definition, because it's too immature, and that's for a program of record. So sometimes maturing an item, a technology, like I did one time for a very sophisticated system suspension for Humvees, up armored Humvees. We really had a hard time getting from the 5 or 6 level, maybe approaching 6, to get the program manager to pick it up. So anyway, it's important to understand where your technology is at. It's important to understand where it fits into the whole product development cycle. Any questions there? Okay. Silence is concurrence. Let me move on. So, a little example of the motor scooter motorcycle. My question, and I'm not answering this one. One of the students has to give me some feedback here. What TRL do you think that is and why? Over.
I would say it's level 7.
Uh-oh, don't know why that switched there. Okay, why?
Well, I think it's at least level 7 because we see the final product. I can't tell whether it's been tested or not, and I can't see it being operated or used. So, so far, it just looks like just a model that might or might not work and pass tests.
Very good. And I think it gets into, let's talk a little bit about the wording on the TRL levels here, if we could. Good point, though. So it's looks like has been operated in what I would consider a relevant environment, excuse me, as a system, right? My voice is going, I do apologize. So level 5, for example, is key elements read subsystems, been demonstrated in relevant environment. Level 6 is the deliverable, the complete system demonstrated in a relative environment. So by the looks of the prototype, it would appear that it's been road tested, if you will, on the street. And so you would say, okay, it's level 6. When you go to level 7, it says final development version of the deliverable. Well, between 6 and 7, there's a whole nother layer of engineering design refinement that has to occur. And it certainly depends on what the end game is, or the end product, if you will. But looking at this prototype, I would say, yeah, it's pretty crude and it hasn't been refined. I'm looking at forks that are made out of wood. I'm assuming that that's not the final end product. But if the end product is have, say some kind of a metal or carbon fiber frame or whatever, I would say between 6 and 7, you would have another design iteration to refine it and make it more robust, manufacturable, or whatever. So to me, it's about a 6 if the final intended use is a more refined item. Does that make sense?
Yeah, that makes sense.
Yeah.
Okay. But it certainly depends on the end item, right? This could be just somebody's weekend thing they put together just because, but I use it as an example of moving towards that, something a little bit more refined, okay? Any other questions? If not, we'll move on, okay? All right. So we'll get back into a little bit more definitions. And so in general rule, the TRL of a system is equal to the lowest TRL of a critical subsystem or component. So if you had a very mature overall system, but a key or critical subcomponent was immature, it's the whole system is qualified as the lowest level. And so where this becomes important, and if you think back to the Jupiter orbital spacecraft, they need to understand where the whole system level maturity is. And if they have a key system, say it's propulsion or navigation, that makes it easy. The navigation system is experimental, not well proven. They need to know that. They need to know that, yeah, they may be able to fire the spacecraft off the launch pad, but it may not be able to go where they need it to go. So from an overall system, it is not as robust and refined performing as they need it to be. So anyway, that's all I want to say about that, is that you always have to look at what the most immature component is. We'll get into some case studies where I've had to manage that, in some case studies where it didn't work so well. Any questions on this? Okay. Yeah, so that's always, this is my so what slide. Yeah, that's nice, but how do I apply it? If I'm an engineer, design engineer, or managing engineer, or even program manager top, how do I apply this? So what if it's a 6? What do I do with that? So it's important as you are, even if you're the designer, you have to understand where your risk lies. If you are more of a manager, if you are a program manager, if you're engineering / program manager, you have to understand where your risks are for your schedule, your cost, your safety. Cost, schedule, performance, and safety are the 4 layers, if you will, that are always competing with each other on any product you're trying to put out there. And so you have to be able to define where your risk is and then what it will take to lower your risk to an acceptable level to move it up the TRL ranks. And with that, one of the techniques, as we'll talk about a little bit later, of managing the risk is performing trade-off analysis. And sometimes it's also parallel prototype development as well. If you do not think you can control your variables well enough, but you're always, as a designer or manager, you're always trading off performance versus cost, or performance versus schedule, or safety versus cost, or even, if you're a very aggressive public company, like let's say Apple is, product launch schedule is extremely important to stakeholders and their share price or their stock price, but they also always have to balance that against cost and safety, and also company reputation, which is so important. I think Facebook is really hurting in that area right now with company reputation and in personal rights and so forth. Not personal rights, but data security and so forth. But all these things are part of the trade space. Nothing becomes purely technical in a practical approach. And when you're doing engineering, it'd be nice if it was, but the rubber needs to meet the road, and you have to have a product at some point. Moving on. So I'm going to get into, excuse me, some case studies about things that I directly were involved with. I don't think we'll have time for all 5. We'll probably get through about 3 if the previous 2 lectures are an indication of how we'll go with this one. And we'll get through about 3. All these, the first 4 items, actually, I guess all 5 of them I was very intimately involved with. So again, none of the photos that I'm going to show you or graphics they're all from the public domain, and that's how I'm allowed to share with you. I just happen to be involved with them. I know the background, so I can provide this or share it with you. So moving on. This was a project I had about 5 years ago, perhaps 2014, so maybe 6 years ago, 7 years ago, excuse me. And we were working on doing some experimentation with additive manufacturing and 3D printing about 7 years ago, and how can we apply this to special operations. And so I was working with Oak Ridge National Lab up in Oak Ridge, Tennessee, and Dr. James Collette up there. And we were looking at body armor and how can we improve the performance of body armor. So, and using additive manufacturing as the technique to do it. And so we were studying the mantis shrimp. If you're familiar with the mantis shrimp, the little circled area, the reddish area, is its hammer fist, and it eats by killing its prey by hammering on it, like mollusks, clams, and so forth. And the little arm, the little hammer fist, travels supersonically subsurface, which is kind of amazing, but it does. And it smashes the shells, and then the shrimp eats the animal inside. So, but it doesn't break down. The hammer fist doesn't decompose. It doesn't wear out. And so on the right side below in the gray, the black and white photos, the electron microscope of the fibrin, or the fiber that comprises the hammer fist. And to the left in yellow is a model trying to replicate that same design. As what you see is the the fibers that are comprised in there are continuously biased ply. They continuously rotate through a 360-degree circle process all the way through. So the hypothesis or concept, if you will, that we had is the hammer fist isn't destroyed by the shock wave. It impacts onto the shell, but the shell breaks. The shell breaks because of the shock wave imparted in it. Because the mass of little hammer fist is too little, but it's the shock wave that imparts it. And it actually puts it into tension, compression, then tension, and it fractures it and it comes apart. So we're thinking, okay, if we, that sample there on the right, lower left, or lower right rather, of the cross section of the piece of titanium that's using additive manufacturing, that's only 1 centimeter thick. I didn't put a scale on it, but trust me, it's 1 centimeter thick. So a little less than a half an inch. And the intent was to shoot that with 9mm ball ammunition and stop it. And the concept is that through impedance mismatch or disruption, we could prevent the shock wave from propagating the shock wave of the impact of the projectile to the surface, and it wouldn't travel all the way through to the back face and then echo back. And so you would never put the material into tension, only in compression. And so we did that by changing the density of the metal, and you can do that with additive manufacturing by the process of either the dwell time or the electronic beam or the laser, and how much powder you put down and what shape you put the powder. And as you can see, we have a hollow kind of honeycomb core, and it worked. And so we could shoot that repeatedly in a lab with 9mm ammo, and it held up. It didn't penetrate through. We had a little back face deformation, as it's called, but well within standards. So interesting little concept we did. So my question, looking at that last little project on biomimicry, what TRL level would you consider that to be? Anybody out there?
At least a 4.
I'm sorry?
At least a 4.
Okay, tell me why. Tell me why.
So it can at least stop the 9mm ammo in a laboratory environment, that given, of course. And I mean, it didn't sound like it was used in a vest, for example. It sounded like it was just used as a simple material in a lab for testing. So I would say 4.
Right. So would you say when you go to a level 5 and it's demonstrated in a relevant environment, to me that says, okay, I've got more of a perhaps different temperature variation. And maybe perhaps it's not a flat plate application that have more curvature to it. Excuse me, more representative of the final product. Excuse me, I really apologize for my voice this afternoon. But I would agree with you, Kevin, that it's about a 4. We shot it a number of times. I think it was at ambient temperature, about 72 degrees with 9mm ball, and it successfully stopped every round. But we certainly didn't go down to minus 22 degrees F to 200, well, about 150 F, and check the whole temperature zone and extremes, especially as the temperatures get lower and lower and lower. Material behaviors change a little bit, especially when the strain rate is really high. So yeah, limited laboratory testing, and it was successful there, which was nice. But this is a little $500,000 project. And I think we can say we successfully got it to a level 4. Unfortunately, we didn't move on with it because, I say unfortunately, we had a competing technology that was also being worked with, a very high molecular weight polyethylene that could stop it as well, but was lighter weight still. And so we put some money into the manufacturing readiness level of the production equipment, and are pursuing that. And with that, with a lighter weight, with equal ballistic stopping power, but lighter weight, we can actually put more armor on the person. So that's what we did. But this was a nice little technology demonstration that reached a level 4. Any questions? Okay, we'll move on then. Here's another effort that I headed up, and this is not nearly as simple. This was a dry combat submersible prototype. We called it the S351. And so in the upper left-hand corner, you can see it motoring around on the surface. That's in the, we built this in Plymouth, England, and that's in the Plymouth Harbor, just motoring around, just doing some basic surface systems checks. Lower left is on a hoist. I don't know if that's, well, there's no water dripping out of it, so that's probably launching it. In front, you'll see kind of a smiley face on it. That's the sonar lens, if you will. It's acoustic lens and so forth. Over to the right, you can see a lower right-hand corner about the number of people by those little figures that it would contain, and it could operate for a few days, number of days subsurface. You can see from the cutaway view or the view upper right-hand corner without the outer fiberglass skin on it, you can see the rib stiffened cylinders underneath. Those are the battery bottles, as we call them, battery canisters, another term. That's where all the batteries are housed for subsurface propulsion, or all propulsion, that matter. So in this case, many of the subsystems were very robust and very mature. For example, the pressure hull. And I wonder if I can you see the cursor when I move it around there? Anybody? Can you see that?
Yes.
I can see it.
Yes.
Okay, so right there is the battery bottles, ring stiffened cylinder. Okay, and you got some O2 flasks here, but the pressure hull, which I'm trying to give you an idea where it's at, all this, and that's the lock in and out chamber. That's a hatchway right through there. That's where divers lock in and out our seals. That's all well understood. Design, materials, fabrication, process, very, very well understood. And so it was made to a very well understood design practice through an international association of classing societies with Germanischer Lloyd, which is now DNV. It's the Danish, I forgot how to pronounce the DNV acronym, but anyway, it's from Denmark. But they have a whole series of standards of constructions and testing and validation. So the pressure hull is very mature, very robust. The battery systems, though, were not. The canister was, but the battery system inside the cells and the battery management system were less mature. And we'll get into more about where they're at later, but I'd give them maybe a 5 to a 6. They certainly weren't time proven, off the shelf system. The sonar as well, which you can, it's really right under this right here. That is a like a bumper, to be honest with you, that's attached to the pressure hull, but it's under here, the sonar. And right here is the window, the sonar window. That's acoustically transparent material. That was also at a lower TRL as the first article prototype build. It was built by University of Texas Advanced Research Laboratory, UTARL, and they're an FFRDC, federally funded research and development center, and they have extreme expertise in sonar design and fabrication. But we were using new off-the-shelf components for the basic design of it. We're trying to leverage the telecommunication industry, so our sonars wouldn't be so darn expensive, and we could be a little bit more of a modular approach, but it's at a lower TRL. It was never used in validated operational environment. So it is about maybe a 5 or 6 as well. But I would think you all would agree that the sonar for obstacle avoidance is a critical component, as the battery were the energy source, critical subsystems for this. So from a TRL point of view, from a system point of view, how would you rank that? How would you What would you estimate that to be from a system point of view? Charles, any idea?
I'd say it's a level 5 then, because as you mentioned before, um, since the critical components are at most a level 5, the system as a whole would only function as best as the component, the critical component.
Yeah, I would tend to agree with you there, because it was obviously, say, both the battery system and the sonar have been more than just a lab environment. We were in the process of, sorry, demonstrating at a level 5, and the battery system did okay. We actually found out that we had a problem with the sonar and it was a highly, highly sophisticated functional sonar. But what we found out was it had great range, but it didn't have great short range. And so what we found out was that within the first 50 meters, for example, didn't see too well. And so you're kind of flying blind for close-up things. But this technology was adapted off what they use in big submarines, big grown-up nuclear submarines. And their operational environment within the last 50 feet, they already know, excuse me, they already know pretty much what's coming. And if they're in very shallow water, like saying coming into harbor, coming back to port or leaving, they have tugboats to guide them out. So they don't worry as much about the close up as we would, because the intended use is slightly different, considerably different. And so where our submersible will go into, let's say, denied waters for the most part, we have to know it's so close. But it's one of those things that we didn't really fully appreciate until we brought something that was designed really for the big submarine world, shrunk it down to size and put it on ours. We realized, oh, we got a gap here. So, but I would agree, the whole system is at about a 5.
I also have a question regarding like who designates the levels, or is it the engineers who are prototyping, or is it like a separate team that reviews it as well?
You know, on a really sophisticated system, I'll just throw like the F-35 fighter out there. And I think that's a Lockheed Martin product. There should be a group of engineers in that program team that are experts at determining a TRL. For our use and the work I've done, you know, I'm not making, you know, $500,000 jet fighters, and nothing I've done. Although, you know, that last submersible you saw was about 50 million all up. But typically there's a very disciplined engineering team in TRL and failure modes that will be doing that to let you know. So what we're talking about here is kind of top level understanding from a practitioner's point of view, and opening you up to what it is and how you should start to think and question, if that makes sense. But yeah, it'll be the engineering team. It sure the heck won't be program manager.
Okay, that makes sense. Thank you.
Okay. So we'll move on to another case study. And I guess I got about 10 minutes left, 11 minutes left. Another case study. This is another one of my projects, the surface planing wet submersible. The first version of this craft, it's a hybrid craft. I was on the design team many years ago, and I patented the surface propulsion system. So a company came along, licensed the patents from the Navy, who I worked for at the time. And this is the next generation of the boat. Very good design from the company, using government money through a congressional ad. Sometimes you call it pork, but we accepted money and they refined the design. Very quiet boat, extremely quiet boat. In fact, if the boat's approaching you, the only thing you can hear is the water slapping off the hull, doing about 35 knots. So pretty impressive design. But the battery system for the subsurface propulsion and you can see, let me move the cursor. There's some control surfaces here for subsurface propulsion, as well as some thrusters here up on the bow. And then there's also some thrusters that pop out of the sides for subsurface propulsion. And so it runs off a battery subsurface. Battery system was not as mature. And so you can see from the planing hull right here, which was aluminum, welded aluminum. The top skin was closed cell foam composite, typical classic boat building materials, well understood. The thrusters were commercial off the shelf. The engine we used in this one was a Yanmar engine that was encapsulated, all very mature design. What wasn't was the battery system, and we were trying to mature it. So what we did we identified it early on that was a lower TRL, and we understood that it was risk. So what we did is we placed in the boat for some relevant testing, very well understood car battery technology. Didn't have much energy density, so it couldn't go but maybe a mile, nautical mile subsurface, but it was safe. We understood it. The risks were minimized. In the meantime, we were developing lithium ion. It was lithium ion cobalt, was a chemistry battery system, which with much higher energy density in parallel. And the idea was to mitigate our risk by doing it in parallel. And once it matured, we would integrate it into the boat. Well, going through laboratory testing, the system, the battery system, we're doing vibration and cold soak, heat soak of the battery system and cycle of charge, discharge, and so forth. It would lose capacity. It will lose capacity and so forth. So we sent back to the vendor, the prime vendor in charge of, responsible for the whole design and fabrication. They send it to their subcontractor to remedy the problem. Yet again, this is about the third time. Instead of sending it back to the laboratory, the government laboratory, to keep testing, they put it back in the boat, which it was never in the boat. So they replaced the very marginally, low energy density car batteries with this, because the member of Congress that granted them the money wanted to take a run at the boat. And so a congressional delegation went down to Marathon to this facility to take the boat out on a Saturday just to see what the money was buying, which sort of makes sense, but we lost control, the government did, of the battery in this case. We didn't have positive control. The vendor put the battery into the boat, took the congressional delegation out on a Saturday, and kind of got beat up, it was rough water and weather, as I was told. Put the boat, came in, cleaned it up, put it into the shop, into their barn, and started to recharge the battery. Well, when it's about 10 o'clock Sunday morning, when it was about topping off the battery charge, it caught fire. The battery did. And the way these batteries catch fire, it's kind of a plasma torch burn. You can't put them out once they start, because they contain their own oxide and fuel. They just need enough heat to start. And it did, and it cascaded through. They pulled it out of the barn, and that was actually a photo that was in the newspaper in Marathon. And it burned. It burned the whole top skin and burned right through the aluminum hull. So this was a case where we as a government and the design team were managing the risk of having this low critical subsystem developed in parallel. The vendor on their own decided to put in it without the authority of the government to do it. And this is what happened. This is an example of what can happen every time. It just depends on the criticality of the subsystem. So with that, from a system point of view, with that experimental battery in it, what TRL level would you consider the whole system to be at that he took the congressional delegation out on? Anybody?
You said everything but the battery was at a higher level of development.
Yeah. It may not have been at an 8, but it was certainly not built on very immature technology. Some of it, for example, the battery canister that this big inline 6-cylinder Yanmar diesel engine was a one of a kind, but it was made out of very well understood components, and all the sealing techniques, O-rings and all that, they used very standard O-ring design techniques. And so while it was new, it was designed under known design process, if that makes sense. So a little bit higher. We didn't have the concern with that.
Okay, I would say as a whole, it would probably be just below a level 5, because when they took it out into that relevant environment with the waves, then the system simply because of the battery failed altogether.
Yeah, it kind of leads you to believe that, right?
Yeah.
And while we were having, as I described, we were having problems on the lab. And because it kept losing capacity when we were doing vibration shake tests, when we were doing hot soak, cold soak, and so forth. So it was a questionable level 4, if you will, that key subsystem. And so right in there, I don't say, I think it was more mature than a 3, but certainly wasn't graduated to a level 5. What we had done previous is we kept a very low energy dense battery in it so we could go out and get the rest of the boat really until level 6, represented of the deliverable and a demonstrated relevant environment. So the rest of the boat, I would say, is arguably level 6. But once you throw that battery, it drops it down to a 4, and that's what happened. And that kind of illustrates why NASA came up with this process, because they were being snake bit with the same issue, is introducing risk into something when you should have managed the risks through a parallel effort. And I don't have much time, so real quick, I'll go to the whole submersible that we talked about before. One of the things that I had a challenge on is because of that, and that was mine, and I owned that problem, unfortunately. I didn't want that to happen to that submersible, burn up in a fire. And so me and the design team or engineering team, government engineering team, this is what we did. We took a three-prong approach to mitigate the risk. We put millions of dollars into silver zinc battery technology, battery management system, and so forth. And that was co-done by the Battelle Memorial Institute and NSWC Crane and Navy Lab. We had another one, lithium ion, that we had hired General Atomics to develop along with NSWC Crane. And then we also explored fuel cells with Siemens in Hamburg, Germany. The fuel cells lost out pretty quickly when we were doing some trade-off analysis, because a couple things, but one was the biggest thing was the global fuel logistics challenge. How are you going to refuel the thing across the world as mobile as this thing needed to be? So we quickly said, nah, it's a little bit too hard to do. So we put money in both 1 and 2 solutions, trying to progress the maturity. And ultimately, we went with lithium batteries because the silver zincs are just such high maintenance that the downtime, and we knew it, but they were safe. But the downtime for maintenance was just problematic over and over and over. But we tried to mitigate it, and we didn't. But this is a classic way you do it. You do some trade-off analysis. Sometimes it's on paper. Sometimes you parallel development efforts to avoid problems like safety problems, a fire, or whatever. It's a classic mitigation trade-off that you do. Does that make sense?
Yeah.
Okay. All right. So I know I'm running out of time. So I got a few more case studies, but don't have time with, but these are some of the main takeaways what I was wanting to present here. TRL is nothing more than a method to have common terms and understanding on how to quantify a level of maturity for a technology, a key system, or it could be the whole system, but dependent on the weakest link, if you will. TRL, along with, and I didn't talk about it, FAMICA, failure modes, effect, criticality analysis. And that's a technique to look at if something fails, how catastrophic is the failure? For example, that battery fire on that hybrid boat. when it failed, it was catastrophic and burned to the ground. Fortunately, nobody was in the building. They were able to drag the boat out and nobody was hurt or killed. But that is very, very, both of those things are used in engineering to quantify the risk constantly, at least within the military. And then another one is you manage your risk. You identify it first, you understand what the criticality of failure is, and then you manage it. And it could be trade-off. It could be you don't do it. Or it could be you do parallel development efforts. There's a lot of things. So you got to understand it. You got to know how to measure it. Then you deal with a trade-off, managing it. And you always have to look at intended use. Something can be very mature for one use or application, but when you put it into a different operational environment, the intended use is different. So it's no longer considered as mature because it never went through a different operational use evaluation. So some things are not as intuitive, and then never overlook safety. This whole process is to get you to think and ask questions about what you're doing, or maybe one day you're going to be in charge of a big, massive thing being developed. Help you ask the right questions so you fully understand, so you don't end up with a burned down boat like I did. But that's it in a nutshell. That's all I can give you in about 45 minutes or so. Any questions? Carl, Davis, any questions?
No, sir. I think that was a very good presentation. Thank you for that.
Yeah, I think you did a good breakdown of the 3 case studies you were able to present.
Okay.
And
all right.
are the other 2 just past this point in the PowerPoint?
Oh yeah, this was, I did a
Okay.
human injury study for 7 years and developed suspension seats for our boats. Was another one, and trying to avoid human injury, and some of the trade-offs you do doing that, and some of it's money, some of it's packaging, and some of it's human injury, and how to understand where those human injury exposure levels are, how to quantify it, and so forth. Did a lot of work with cadavers and measurements and so forth. Very interesting work. And fortunately, the team I put together was able to identify at least a relative sweet spot of goodness. And systems like these, seats like these are being used. I think the first slide in the presentation, somebody said something about, oh, neat boat. That's the CCM combatant craft medium that we have in inventory with the SEALs and SWICs. And seats similar to these are in there. This technology, this concept has been now proliferated within all of our boats. So this early on development work kind of worked, if you will. So anyway, a few case studies. That's an intended use case study there with that. That's in Norway. Actually, a friend of mine died on that boat because it was designed by an Italian company that make offshore racing boats, and they try to use it as a prototype in evaluating for special operations. And the way they operate boats are very different in special operations that is compared to racing boats. And it threw a friend of mine, close friend of mine, off the back, and it killed him. So understanding the intended use of things, they don't translate one-to-one. It's safe in one environment, it'll be unsafe in another. It doesn't work that way. So anyway, sorry. We'll leave it at that. Any other questions? Professor
Can you
Traum?
reiterate? Oh, I'm sorry.
Yeah. No, please.
Can you reiterate what you meant when you said that a product is refined?
Ooh, exactly how did I say that? When I talked about refined, on that last case study, or just in general?
In general, you talked about it before when we were going over the TRL examples.
Yeah, well, when I use the word refined, I mean matured, right? Additional engineering has been putting into it, refining the design for, it could be durability, reliability. It could be on some systems, electromagnetic interference from a radio system or another electronic component. It could be corrosion. For example, those boat seats right there. EMI testing, we did that because the radios would actually affect the electronic controls of the suspension. Corrosion in this system had to be gone through and looked at crevice corrosion, material selection, and so forth. So when I talk about refinement, I'm talking about going through all those different areas of a quote product's design and have they been refined to be optimized for the given intended use. Some of it's weight, some of it's cost. I can tell you the control boxes on this thing. Right here is one of them. It's got accelerometers in it. It's got a potentiometer in it and a variety of other little electronic circuits in there. We made those in the United States, but for commercial use, those are made in China because of supply chain issues and alike. So there's levels of refinement that you make, and it's really kind of optimizing it for its intended use. Does that answer your question?
Thank you. Yes.
Okay.
Okay, so just for the interest of time, I think we'll probably wrap it up there because we're 5 or 6 minutes over. But I just want to thank Mr. Martin for coming and presenting virtually. He's actually here on campus. Gave 2 in-person presentations today, all the way up from Tampa. And this one, of course, is online since we're the online section. But I want to just reiterate how much I appreciate you coming up here and interacting with our students and giving them a taste of what goes on in the real world with respect to TRLs.
I enjoyed it. Thank you so much.
All right, thank you.
Thank you for the presentation.
You're welcome. Thank you for being here, and also expect you all to do good things for our country. Okay.
Thank you.